Dear students, very good afternoon. So now I'm going to explain about the one more experiment, that is experiment number 5, microwave test bench. So this is operating in the expand of operation. Expand of operation means frequency at this band which is operating between the 8 gigahertz to 12 gigahertz. Okay, and in this experiment you are going to determine what is the frequency guided wavelength VSWR of the microwave signal, both theoretically as well as practically. You are observing the microwave bench setup, which consisting of the klystron power supply. First one is the klystron power supply, and followed by the klystron tube. Next isolator, then attenuator, variable attenuator, and variable frequency meter, slotted line carriage, and terminator, then VSWR meter. See here we are also using the CRO to measure the microwave signal. Same thing which is mentioned in the black diagram also. Whatever is there in the experiment setup, same thing which is mentioned in the black diagram also. KPS stands for klystron power supply. Then 2K25 is the klystron tube, klystron mount, followed by the isolator, variable attenuator, variable frequency meter, then followed by detector mount, which means slotted line carriage, and CRO. So the function of each block I want to tell you once again. The klystron power supply which provides the microwave signal. That microwave signal which can be emitted by the klystron tube. Then isolator which allows the signal to flow in the forward direction, blocks the signal to flow back in the reverse direction. Attenuator used to control the flow of power in the waveguide. The frequency meter used to measure the frequency of the microwave signal and used to measure the dip frequency. And detector, then slotted line carriage can be used to find out the wavelength as well as VSWR. And detector, the mount, that is used to detect the signal that can be observed in the CRO or measured in the CRO. See, we have to take some precautionary measures before switching on the devices and power supply. So we have to set the cooling fan to cool the klystron tube. See, otherwise the klystron tube gets heated and maybe getting damaged. So if you are not cooling that klystron tube, and then we have to set before switching on the klystron power supply, we have to set the beam voltage to minimum and repel voltage to be maximum. Then AM frequency knob at mid position. Similarly, AM odd amplitude knob also at the mid position, and voltage current switch of the display to current position, and this one the voltage knob to the off position. See, then what we have to do in the setup also, we have to keep that frequency meter to be maximum, and attenuator to, we have to say adjust the attenuation to 15 decibels. So and then keep the slotted line carriage to the maximum position. Okay, these are the initial settings can be done before switching on the device. So now this is the klystron power supply, as I told you. We have to adjust now, switch on the klystron power supply. So then adjust the beam voltage position around 290 volts. So then turn the knob to the beam voltage position and check it out. If it is not 290 volts, then increase the beam voltage so that it reads, increase the beam voltage so till the 290 volts is appeared on the klystron power supply. Then change the knob to the repeller current position, beam current position. The beam current should be around 15 milliamps. Then turn the knob to the beam repeller voltage position. Then what you have to do, so initially if we turn onto the repeller voltage position, it shows around 220 volts. Then reduce the repeller voltage until you get the maximum square wave on the CRO. So once you get the maximum square on CRO, that is the first mode of operation. So afterwards what you can do, tune the frequency meter until you observe the dip in the microwave signal. So that is called as the dip frequency or the resonant frequency or the cutoff frequency. that is your practical frequency. Understood? Practical frequency. To measure the theoretical frequency, we have to use the relation C is equal to F lambda, or lambda is equal to what, C by F. This we have to use. And then we can find out the theoretical frequency. How to find the theoretical wavelength and theoretical frequency? Dear students, in the slotted line carriage, so the position is initially in the loaded load position, right? Load side, right? Then move that slotted line carriage from the load end to the generator end. When you are moving the slotted line carriage from load end to generator end, you are observing the crest and troughs in the sphere. Crest and trough means maximum, minimum, maximum, minimum, minimum, maximum, maximum, minimum, maximum, minimum you are getting. See, either you can take two maximum or you can take two minimums. Okay, so I'll tell you how to take two maximums. For example, at the load end, when you are moving, you are getting first maximum. So again, if you move, it reduces. Again, if you move, again it increases. If you move, again decreases. So alternative crest and troughs you are getting. Either you can take crest or troughs, means either two maximum or two minimum. So first maximum we can find out using the relation x1. x1 is the first maximum value, which can be determined using the formula MSR plus CVD into LC. MSR is the main scale reading and CVD is the coincident vernier scale division, and LC is the least count. Least count is always 0.01 centimeter. So what happens when you are moving the slotted line carriage? The slotted line carriage having the main scale reading and the coincident vernier scale division, and you have to find out main scale reading and the CVD. Substitute over there, you will get the x1 value. Similarly, move the slotted line carriage to observe another maximum on the CRO. See, that can be denoted by or indicated by x2. x2 also determined using the same relation. Then what happens once you determine the x1 and x2, use the relation lambda g is equal to twice the difference of x1 and x2. So why we have to find out x1 and x2? I will tell you, dear students. Because we have the one formula to find the what is that theoretical wavelength. 1 by lambda naught square is equal to 1 by lambda g square plus 1 by lambda c square. So lambda g is the guided wavelength, which is nothing but twice the difference between x1 and x2. Okay, so then what is x1 and x2 means? The first maximum is x1 and second maximum is x2. Okay, then lambda c is nothing but 2a, where a is the maximum width of the rectangular waveguide, which is 2.3 centimeters. Then lambda c is equal to a, nothing but 2 into a is 2.3 means 4.6 centimeters you are getting. So next substitute this lambda c and lambda g in the equation, you will get lambda naught. Lambda naught is the cutoff wavelength of an microwave signal. So this is your theoretical wavelength. From this theoretical wavelength, we can find out the theoretical frequency as f is equal to c by lambda naught. Okay, c is equal to f lambda. So then f is equal to c by lambda naught. Okay, c is nothing but 3 in 10 centimeter per second. It is velocity of light in the air. So from that we can get the value of the theoretical frequency, and VSWR can be determined using the relation Vmax by Vminimum. When you are moving the slotted line carriage from the load end to the generator end, you will observe minimum amplitude plus another maximum amplitude. So note down that maximum, voltage minimum, nothing but minimum amplitude and maximum amplitude. Divide maximum amplitude by minimum amplitude, you will get VSWR. So this is your theoretical VSWR. To find the practical VSWR, instead of connecting the probe to the CRO, connect that probe to the VSWR meter and keep the gain of the VSWR to maximum. Then for the same input signals, so you are observing the VSWR as 1.1 something. Okay, that is our practical VSWR. And finally, you have to check whether the theoretical readings are matching with the practical readings or not. Okay, so that's all about this micro test bench experiment. So thank you for watching this video.